Hello. The modern information age has given rise to information junkies who need to be online all the time. In the last lecture, we have discussed the communication media, the transmission media like coaxial cable, optical fiber, twisted pair are of no use to these people. They want to communicate while they are traveling by car, they are in the aeroplane, while they are sitting in a meeting. For them, the solution is wireless communication. Now, this wireless communication can be done by using unguided transmission media, which is the topic of this lecture. Before I consider in detail the unguided transmission characteristics, let us have a look at the electromagnetic spectrum in use for communication. It starts from 10 to the power 4 Hz to 10 to the power 6 Hz, which can be divided into several important bands: radio, microwave, infrared, and UV. From 10 to the power 4 to 10 to the power 7.5, we can say it is radio, and then from 10 to the power 7.5 to 10 to the power 11, microwave, and from 10 to the power 11 to 10 to the power 14, infrared, and 10 to the power 14 to 10 to the power 16, it is ultraviolet or UV. Now, in the radio frequency range, the twisted pair and coaxial cable operates, which you have discussed in the last class. Optical fiber operates in the range of 10 to the power 4 to 10 to the power 15. On the other hand, we shall be focusing on the wireless communication based on unguided transmission techniques, which uses radio communication, broadcast radio, satellite, and the infrared. So we shall be focusing on these three frequency bands for wireless communication. First one is broadcast radio. The frequency range is 30 megahertz to 1 gigahertz. Then microwave, which is from 2 gigahertz to 40 gigahertz. As you know, megahertz m is equal to 10 to the power minus 6 megahertz. Mega is 10 to the power minus 6, 10 to the power 6, and gigahertz is 10 to the power 9 hertz. And then infrared, the frequency range is 3 into 10 to the power 11 to 2 into 10 to the power 14 hertz. So we shall be concentrating on wireless communication using these three frequency bands. First of all, let us consider the broadcast radio. In broadcast radio, we are using 30 Hz to 1 gigahertz of frequency range. In this frequency range, the electromagnetic signal travel long distances. So signal travel long distances. We can communicate over a distance of even hundreds and thousands of kilometers using the radio wave, radio signal. Another important feature is the signal is omnidirectional. Omnidirectional. That means it propagates in all directions. As a consequence, it can be very easily used, it can be readily used for broadcast communication. Then third feature is, for this ionosphere, ionosphere is transparent. That means the signal which reaches the ionosphere, the upper layer of the atmosphere, a signal goes through it, it is not reflected back. As a consequence, the communication has to be line of sight. You have to perform line of sight communication. Let's see how it can be done. You can have an antenna. This is the base, rigidly fixed, and from this signal propagates in all directions. We can set up small antennas in different places at different distances to receive this signal, giving you broadcast communication. And this is because of the line of sight communication, the range will depend on the height of the antenna. There is a relationship between the height and the distance over which the communication can be done because of line of sight communication. That is, D is equal to 7.14 root kh, where D is distance in kilometer from the antenna, between the two antennas, transmitting antenna and receiving antenna. H is the height of the antenna, height of the antennas in meter. This factor K is known as adjustment factor, and typical value is 4/3. This adjustment factor is necessary because it has been found that the signal is not perfectly line of sight. The signal gets reflected through the air along the surface of the earth, so you get little longer distance because of this refraction, and that's why this adjustment factor is necessary. Now, what is the characteristics of the signal, or in other words, in this particular case, what kind of attenuation the signal suffers? For guided transmission media, not only the signal is attenuated, but different frequency components are attenuated by different amounts. Here it is not that situation, because we shall be sending modulated wave, the carrier will be sent, and we have to look only the attenuation factor, and attenuation has been found to be is equal to 10 log 4 pi d by lambda square. So we find that as the distance increases, the attenuation is more. Longer the distance, more is the attenuation, and also if the wavelength is longer, attenuation is less. That means high frequency components are attenuated more than the low frequency components. Now, apart from this attenuation, another problem in this frequency band is interference. The signal is transmitted through different paths. Sometimes it is reflected from solid objects like a building. Sometimes it is reflected by an airplane moving in the sky. And we find that two signal reaches, maybe one signal is of lesser strength than the other, and these two leads to interference. There is a common experience of observing ghost images on the television, and that arises because of interference of two signals. One signal is directly coming because through the line of sight communication. Another signal is coming through reflection from a building or airplane or some big trees or some solid objects. Common application of this broadcast radio are for radio broadcasting, Doordarshan, I mean our All India Radio you can say. Then it is also used for television communication, television broadcasting, Doordarshan. For our data communication purpose, one popular application is packet radio, which we shall discuss in detail later on, and where we use the broadcast radio technique. Now let us focus on the second approach, the second frequency band, that is your microwave transmission. Microwave transmission can be broadly divided into two types. One is terrestrial microwave, another is satellite microwave. Now it has been found that above 100 megahertz the wave travels in straight line. So here also we have to use line of sight communication. And another important property for microwave signals in the range of 2 gigahertz to 40 gigahertz, the signal can be focused with the help of an antenna, and we can make use of this property. We can focus a signal, and this focused signal can be sent to another antenna in the at the other side. And so here the main properties are signal travels in a straight line, therefore we have to use line of sight communication, and we can make use of this property that signal can be narrowly focused. And this particular feature will help us to improve the signal to noise ratio of the signal. Now let us consider these two, terrestrial microwave and satellite microwave, one after the other. First, the terrestrial microwave. In this case, on the surface of the earth, you can set up two microwave antennas very rigidly on the surface of the earth. This antenna is in the form of parabolic dish. This is of the side of a dish of diameter 10 feet, and this is another antenna which is also set up on the surface of the earth, and then you can have line of sight communication between these two. And in this case, again the curvature of this earth, or curvature of the earth, because of the curvature of the earth, the signal will be obstructed if the two antennas are little far apart, or the height of the antenna is less. So the same formula, d is equal to 7.14 root k by h, is applicable in this particular case. And if we want to communicate over longer distances, we have to use a series of microwave relay stations. That means instead of just two antennas, we can have a number of relay stations in between. That means from the transmitter, an intermediate microwave tower will receive the signal, amplify it, and retransmit. For example, for communication from Calcutta to Kharagpur, if you have come by train, you must have noticed the microwave tower at Paskuda. So that microwave tower at Paskuda acts as a relay station. So by using such relay stations at regular intervals, we can perform long distance communication, maybe from Calcutta to Bombay, Calcutta to Delhi. That communication can be done, but we shall be requiring a large number of intermediate relay stations in between. And so a series of relay stations can be used. Typically, the distance between the relay stations varies from 10 kilometer to 100 kilometer. For example, if we use this formula, d is equal to 7.14 root kh, if the height of the antenna is say 100 meter, then if we substitute it is here the value of h, we can get d is equal to 80 kilometer roughly. And from this equation we can see an antenna height of 100 meter for both the antennas, we can have a distance of 80 kilometer, and that's why you can have a range of 10 kilometer to 100 kilometer. In this case, apart from the attenuation due to distance, which is again follows the same formula like 10 log 4 pi d by lambda square. Same formula is used for attenuation purpose. Here also we see as the distance increases, the signal strength goes on decreasing at the rate of square, and also as the signal attenuation is less for shorter waves. That means at higher frequencies the signal attenuation is more. Another problem in this case is rainfall. When there is a clear sky, there is no rain, attenuation is less. In rainy season, attenuation is more. Because of rainfall, attenuation is more. And lastly, the multipath interference, as I told in case of your broadcast radio, same thing happens here, multipath interference. But multipath interference problem is less severe in terrestrial microwave because you are sending a focus signal, and unless something is in the line of sight, this multiple interference cannot take place. But in broadcast radio, this is very common. It leads to fading, it leads to ghost images and various other things, which cannot happen here. Now, this terrestrial microwave, we find that the height of the antenna is restricting the distance between two stations. What can be done to increase the height of the antenna? We can use a repeater in the sky that is precisely done in satellite communication. In satellite communication, what you do, you put a repeater in the sky, and by doing that you can cover a longer distance between two antennas, two stations, receiver and transmitter. Let us draw the diagram of a satellite in the sky. I am not good in drawing, so these are the various solar to pick up solar signals. These are used solar plates, and then you can have parabolic antennas like this. And on the surface of the earth, you can have ground stations focusing the signal. Now you will find that two signals are used, uplink and downlink. You can have another antenna here. This is known as uplink signal, which is going upwards, and another signal is used to avoid interference, that is called downlink. So this is the basic physical structure of satellite communication. Now here the antennas have to be stationary with respect to this repeater. How that can be achieved? That can be achieved by putting the satellite in the geostationary orbit at a distance of about geostationary orbit at a distance of about 35,784 kilometers above the surface of the earth. That's a very long distance, and you can imagine what is that's a very long height. So you can imagine the distance that can be covered by this. Now let us talk about the frequency bands. Normally two separate frequency bands which are used for uplink and downlink, and 4 by 6, that means 4/6 stands for the uplink and downlink frequencies. For example, 3.72, 4.2 gigahertz is used for your uplink, and 5.925 to 6.425 is used for downlink. It seems I have put in the wrong way. I believe 3.7 to 4.2 gigahertz has to be for downlink. This is higher frequency that is used for downlink. Sorry, it's okay, uplink. Now similarly you can have the other frequency bands like 12 by 16, because the number of satellites is increasing and the number of satellites is restricted. For example, whenever you are using this 4 by 6 frequency band, then you have to use 4-degree spacing between two satellites in the equatorial plane. That means you can have maximum of 360 by 4, that is equal to 90 satellites at most. On the other hand, if you use this frequency band, then the spacing can be 3 degree between two satellites, and you can have 360 by 3, that is 120 satellites. And because of this long distance from the surface of the earth, there is a long propagation delay. And delay is about 1/4 of second, the round trip delay. You can calculate this delay based on the speed of light, that is 3 into 10 to the power 8 meters per second, and based on that you'll find that for this particular distance the round trip delay will be roughly 1/4 of second. Now coming to the applications, for terrestrial satellite, terrestrial microwave, it is used for long haul telecom, long haul telecommunications, for telephony, for between two stations, between two exchanges at a longer distance. It is also used for short point to point link between buildings. For example, in Calcutta, you have a number of telephone exchanges. In the early years, they were using coaxial cable, underground coaxial cable, but because of digging and various other problems, in the rainy season particularly, the communication used to be disrupted. Now in most of the situations, they have put microwave towers on the roof of a building to link the telephone exchanges. And typically the frequency band that is used for this purpose is 22 gigahertz. And this particular is used for the long haul communication, is used for voice, that means telephone, and TV broadcasting. Coming to the application of satellite microwave, there are many interesting applications. First of all, long distance telephony, intercontinental telephony can be done by this. Second useful application which is coming up is private business network. In private business network, suppose a particular enterprise, maybe multinationals, have their offices in different cities in a country, in a big country like India or USA. For their private communication, they can make use of this satellite communication, and which is becoming very popular. Finally, a low-cost solution has been invented, which is known as very small aperture terminal, VSAT, where the size of the antenna is much smaller, and using this VSAT technology, you can have you can have a number of the basic organization will be like this. You will have a satellite. Let's assume this is the satellite. Ku band satellite it is called. Then you will have a ground station which will act as hub, and a number of VSAT antennas, and this ground station will be used as a hub. Through this the communication will be done. All these subscriber stations communicates through this hub. So that means all communication is, suppose this station A wants to communicate with B, it will send to this hub, then B will communicate, will receive it through this hub. So in this way, using a central hub, all the other stations, ground stations, can communicate through satellite. And this particular technology is becoming very popular. For example, in our country, that ERNet, Educational Research Network, uses this particular technology. And there are various other applications which are emerging based on this VSAT technology. Now, coming to the last frequency band, that is infrared. Which are used for short distance communications. We have seen the frequency range of infrared, which is not visible light, from 10 to the power 11 to 10 to the power 14, and in this frequency band the usable band is 3 into 10 to the power 11 to 2 into 10 to the power 14 Hertz. And in this particular case, you use modulated infrared signal for communication purposes. Main feature of this is, since it is some kind of light wave, light signal, it cannot penetrate walls. For example, we have seen in broadcast radio, the signal can penetrate buildings. As a consequence, the broadcast radio is suitable for both indoor and outdoor applications. On the other hand, in infrared, the signal cannot penetrate wall. It can be reflected by wall, but it cannot penetrate wall. So all the communication has to be restricted within a room. And it is also relatively directional. And it is very cheap, easy to implement, and that's why it is now widely used, or you can say applications. It is widely used in your remote control, of TV, stereo, VCR, and other home appliances. Actually, as the signal goes from long wave towards the visible light, it behaves more like light rather than radio signal. You can perform a simple experiment. You can try to stand between the TV and the remote control and see whether the signal, infrared signal, passes through you or not. This is also an advantage, because the signal does not go out of the room, and as a consequence you have higher security and that can be used for suitable applications. For example, it can be used for indoor LAN or wireless LAN implementation. You can have a number of computers with infrared facility which can be connected to a LAN without physically connected by twisted pair of wire or optical fiber. So you can move around little bit within the room, and it provides you higher security, because the signal does not go out of the room, and this gives you the advantage of no eavesdropping, as it is possible in various other communication media. Now, this has led to the facility that for infrared communication there is no need for licensing. And you can use it anywhere you want, and that is the reason why infrared communication is becoming more and more popular in home appliances, and the wireless indoor LAN is gradually emerging. It will become popular in future. Now let us, before I conclude, let us look back to satellite communication. We made some mistake. Let us correct it. If you remember, I told that this 3.7 to 4.2 gigahertz is used for uplink, but that is not true. This is used for downlink. I had some hesitation, and this 5.925 to 6.425 is used for uplink. One possible reason for this is, as you know, this 3.7 to 4.2 is of lower frequency than this one. As a result, it has got higher wavelength, and as you know, this particular signal will be less attenuated than this signal. So, since in the satellite the power is taken from solar cells, the transmitter will not be of higher power. On the other hand, the ground station can have higher power. So we want less attenuation, better signal to noise ratio. To facilitate that, this lower frequency is more suitable for downlink, and higher frequency is commonly used for uplink. Another point which I missed, in a single satellite you can have several such antennas communicating at different bands. These are called transponders. These are called transponders. So a satellite can have several transponders communicating at different frequency bands. Coming to the application, I missed out one very important application with which all of you are familiar, that is use of satellite for TV communication. Nowadays, many TV broadcast stations have been set up in remote areas. Those are known as low power transmitters or LPTs. And in the radio, when you are watching TV, you will find that this LPT has to be turned off now, you have to go for other things and so on. These LPTs, low power transmitters at remote places, are picking up TV signal through satellite. So in a big country like India, and where there are very remote places, you have to use this satellite communication to receive the signal, and then you can broadcast it over a local area. That is being done, and that's how in our country you have been able to achieve a very wide coverage, more or less throughout the country. A TV communication is possible from the same Doordarshan. Same Doordarshan channel can be seen from remotest parts of the country. Before I conclude, another point I should emphasize. We have seen that there are two basic categories of communication. One is using guided media, another is by using unguided media. When you are using guided media, the transmission characteristics is fully decided by the transmission media. The attenuation, distortion, and various other things that happens is fully dependent on the transmission media. On the other hand, in unguided media or wireless communication, the antenna plays a very important role. And the antenna decides whether it will be omnidirectional, it will be point to point, and also the characteristics of communication is controlled or decided by the antenna. So we have considered, again we can look back to this electromagnetic spectrum, different types of guided media and unguided transmission characteristics by using coaxial wire and fiber optic, twisted pair. These three are guided media operating in different frequency bands, and radio communication, particularly broadcast radio, microwave, and infrared, these are used for wireless communication. If you look at the frequency bands, higher the frequencies, you get higher bandwidth. So we are gradually moving towards fiber optics. Most of the guided media in future will be based on fiber optics to achieve higher bandwidth. On the other hand, for wireless communication, most of the signals will be in the range of microwave. Of course, infrared can be used only for indoor communication within a room, but for long distance communication, radio and microwave is preferred because of higher bandwidth. So we conclude this lecture discussing various types of media. Later on, we shall see how they are used in wide area network and local area network. Thank you.